RSA, the asymmetric encryption algorithm, as we've seen in previous weeks, it stands for Reverse Chimere-Alderman, and it's an algorithm used to encrypt and decrypt messages, and it's an asymmetric cryptographic algorithm, and we use a one-way function that computes, and generating this is quite easy once we know the steps. However, reversing it's very difficult, and an equivalent system was created in the UK apparently before they invented it in America, but it wasn't declassified by MI6 or whatever until 1997. Although they could just say that about anything, couldn't they? They'd be like, oh yeah, we invented that before you, just didn't declassify it. So apparently this bloke here invented it before they did. So he says, or so the British government say. So, things we need to know for the algorithm. GCD, the greatest common divisor, relatively prime, Euler's totient function, modular arithmetic, and how to find E and D. So, the GCD is just a divisor shared between two numbers. So, for example, if we have two numbers 12 and 20, the greatest common divisor is 4, because 4 is a factor of both. Because we're interested in the greatest common divisor between two numbers being 1. And that means that those two numbers are relatively prime, or co-prime. So a prime number is just a natural number that's not a product of two smaller natural numbers, that doesn't have a factor other than itself or 1. The other type of numbers we have are composite numbers. Okay, little bonus answer, semi-prime is just the product of two primes. So relatively prime, or sometimes co-prime, is when two integers share a GCD of 1. So for example, 14 can be divided by 2, 7 and 14 and 1. 25 can be divided by 1, 5 and 25. So the common divisor between those two is 1, which means that 14 and 25 are co-prime. Okay, 14 and 21 are not co-prime because they can both be divided by 7, so they can't be co-prime. And we need two numbers to be co-prime if we want to find the modular multiplicative inverse as 1. Okay, in order for that to happen, they have to be co-prime. So it's easy to find a number that's co-prime, and I'm going to show you a website where you can list the factors of a number quite easily. So you just list out the factors, and if they don't share any common factors, then they're co-prime. So here we go. 20 has all these factors here. 1, 2, 5, 10, 20. Now none of these are co-prime with 20. 3 is though, because 3 isn't a factor. Okay, their GCD is 1. Same with 12. 5 is co-prime with 12. So another thing we need for the algorithm is the totient function, and that's really easy to work out. We just get two numbers that are prime, we take away 1 and we get the product of those two numbers, and we call that in the algorithm phi. Then we have the modular arithmetic. So we just need to think about modular arithmetic as numbers wrapping round. Okay, so here we have a mod clock, mod 4. So we can only ever have answers from n minus 1, 0 to n minus 1. So if we're dealing with mod 10, we can only have answers from 0 to 9. Okay, and n being the mod. So here's an example of it laid out here. We go, so in mod 6, if 6 was n minus 1 would mean we can only have numbers from 0 to 5. Okay, the 6 possible answers, one of them's 0. The highest number we can get is 5. Now, as I said before, if I said to you, the question is something mod 5, and the answer is 4, it's very difficult for you to tell what mod it is, because it's very difficult to tell how many times we've gone round this clock here. Okay, very difficult to tell. So that's why we use this modular arithmetic. Now, these integers here, okay, are all give the same answer. So we're working in mod 5 here. So we have 0, 1, 2, 3 or 4 possible answers. And for example, 5 mod 5 is 0, 10 mod 5 is 0, 15 mod 5 is 0, 20 mod 5 is 0. So those numbers are said to be equivalent or in the same class. And an interesting property of this equivalence class is that what we can do is, if I said to you, what's 26 times 30 mod 5? You would be like, well, that's a very hard question. Well, what you can actually do is you can reduce the class down to any number in the class behaves the same. So I said, what's 30 times 26 mod 5? We can reduce 30 to 0 and 26 to 1. So it's actually the same as what's 0 times 1 mod 5. All the numbers in the class give the same result when multiplied. So 0 is the same as minus 30 and 1 is the same as minus 34. Okay, we're always going to get the same answer when we deal with numbers in the class. So that's a useful property of these equivalence classes. And we can only ever get these 4 answers here. And multiplying any number in this class by any number in this class is just the same as multiplying 0 by 2. Okay, so for example, if we multiply 0, okay, by 27 mod 5, it's the same as doing 0 times 2 mod 5. So what do we need for this algorithm then? So we need any 2 prime numbers, p and q. N is going to be the product of those two. Phi, we're going to use this totient function, p minus 1 times q minus 1. And then we can use those to calculate E and D, the encryption key and the decryption key. Sometimes it's called the encryption index or the decryption index. Let's run through a simple example. So hopefully by this point in the class, everyone's fine with the concepts of P, Q, N and Phi. Okay? So P and Q are any 2 primes, and we use those to calculate N and Phi. Okay? So N is really easy. N's just P times Q. And Phi is really easy. Phi is just P minus 1 times Q minus 1. So those are straightforward, okay? These can be calculated by any school student of simple maths, okay? So step 2 is figuring out E, okay? Now to figure out the encryption key, we're going to list out the factors list out all the factors of Phi. Okay, so Phi is 20. Here's all the numbers that can be divided by Phi. There, okay? 20 can be divided evenly by 1, 2, 4, 5, 10 or 20. Okay. So we then have to list out the prime numbers from 1 to Phi. Okay, and we can figure out E, the encryption key, by just picking a number that's not in the factors list. So it has to be a prime from 1 to Phi, but it cannot be in the factors list. So it can't be 2, because 2 divides evenly by 20. It can't be 5, because 5 divides evenly by 20. But it could be any of these other ones, and I've highlighted those in green to show that it could be those, and I've highlighted the ones in red to show that it can't be them. Okay, so we'll choose, because we're working with very small numbers deliberately, we're going to choose 3. Okay, because 3 is the lowest prime number from 1 to Phi that isn't a factor of Phi. Okay, that's the key. Can't be a factor. Can't be a factor of Phi. Why can't it be a factor? Well, because if it's a factor, then the algorithm's not going to work. So really, we're picking a number that's co-prime from these 2. Okay, now, so let's move forward. So now we've got E is going to be 3 in this implementation. So I've listed the numbers up the top here. And then to calculate D, as we've done, we just need to solve D times E mod Phi equals 1. Okay, and as we've seen in previous examples, we all should know by now that 21 is the answer. Okay, so 7 times 3 gives us 21, mod 20 equals 1. So D is going to be 7, okay? And I've worked through the examples one at a time, and I'm going to show you on the next slide. And this is known as the modular multiplicative inverse, okay? And in order for this to happen, the numbers need to be co-prime. So here we go. Here's me working them out one at a time. 1 times 3 mod 20 is 3. Then we've got 2 times 3, which is 6 mod 26. 3, 4, 5, 6, all the way until we get to 7. And we do 7 times 3 gives us 21 mod 20. And that gives us a 1. And there we go, we got D. So with that, we now have all the numbers we need for the algorithm. Okay? So, first example, I've listed our values for the algorithm up here. Okay, so we have P and Q that we started off with, N and Phi, E and D. Okay, now, the public key is E because E is the encryption key. Okay, and the decryption key is D. Alright, so encryption key is E, decryption key is D. So what we're going to do is we're going to calculate, okay, well we're going to encrypt a number now, and that number we're going to encrypt, a nice low number, is 4. Okay, so what we're going to do is we're going to take 4 and we're going to call that M. That's our message that we're going to send over the network. So we're going to do 4 to the power of the encryption key mod N, 4 to the power of the encryption key mod N. So I'm going to work that out. That would be 4 times 4 times 4. So 4 times 4 is 16, times 4 is 64. And then we're going to do 64 mod 33. Now that's quite a hard sum to do, so let's get the old calculator out for that. We're not going to 64 mod 33. That's going to give us 31. So 31 is our encrypted value. Sorted. Okay. So let's send 31 over the network. Okay. So we've encrypted it with our public key, Bob's public key, right? And we're going to send it to Bob now. We're going to say, I've used your public key, Bob, and I've encrypted a number. I'm going to send this over to you. And he'll say, thank you, Alice. I have received the number 31. Now I shall decrypt 31 with my private key, which in this example is 7. A very, very low number. Okay? So all we need to do is take our message, which is 31, okay, and we're going to say M to the power of D mod N, and just work that out. So let's plug the numbers in. 31's our message, to the power of 7 is mod N, mod 33. So let's get the calculator to work that out, because that's a very hard sum to do unless you're super good at maths. So let's do 31 to the power of 7, okay, and that's going to give us this big number here, huge number, okay, 31 to the power of 7, and let's just do mod 33, mod N, mod 33, and this is going to be the decrypted value, okay, so there we go, it's 4, there's the answer. We've decrypted it with the private key and we've got the answer back. So that shows that we can encrypt with E to the power of M to the power of E mod N, and we can decrypt with M to the power of D mod N. Okay, so let's work through P and Q being 7 and 11. So 7 and 11. So the first thing we'll do is we'll work out N. So hopefully we can do that in our head. 7 times 11 would be 7 times 11 would be 77. Okay. Then we need to work out this phi. And to work out phi, we're going to do P minus 1 times Q minus 1. So 6 times 10. We can do that in our head, hopefully. 6 times 10, 60. So there's the easy ones. Okay. Now we need to get out some of these calculators out. Okay. So what I'm going to do is I've got a primes lister here. Okay. and I've got oh, they're going to ask me several surveys and things. Found this primes lister here, but it's full of it's full of malware and like pop-ups and spyware, but it'll do for our purpose as long as we don't mind seeing a lot of advertising. First thing we need to do, okay, after calculating P, Q, N and phi, which are easy, simple arithmetic, we're going to work out E. So we need to find a prime from 1 to phi that's not a factor of phi. So let's take phi as 60 and find the factors first of all. So I've just put that into this calculator. Here's the factors, okay? And then we're going to take prime numbers from 1 to 60, generate prime numbers list, give it a second. So there we go, so there's the primes, okay, there's some advert for some weird thing down there, and here's the factors. So what we need to do is find a prime that's not a factor. So here's the primes, right? 2, 3, 5, 7, 11, and let's have a look at the factors. The factors are 1, 2, 3, 4, 6, 10. Let's go back to the primes list. So we could choose 13, because 13 is a prime, but it's not a factor. Okay, it can't be a factor, but it has to be a prime from 1 to 60, because 60 is 5. So I'm going to choose 13 as our prime here, because I said we're going to ramp the numbers up a wee bit. So E is going to be 13. So all we need to do now, okay, is pick D, and to get D, we just need to solve that classic conundrum, okay, which is D times E mod phi equals 1. Okay, and so we already know what E is, so we're going to have question mark. So you know what I'll do? I'll grab a Sublime text window here so I can type this in as we go. Should be here somewhere. Here we go. See, I've been messing about with some dates there. So we're trying to solve D times E mod phi equals 1, and we already know, what do we already know? We don't know D, so we'll call that question mark, times 13 mod 60 equals 1. So something times 13 mod 60 equals 1, and whatever that something is, that's D. So I actually found a useful wee calculator here called a mod inverse calc. Okay, and if we put in, so this tool computes the multiplicative inverse. Right, so there we go. So because 13 and 60 are co-prime, it works. There is a modular multiplicative inverse of 1. So there we go. So 13 times 37, okay, mod 60 gives us 1. So D is going to be 37. Okay, so back to the algorithm, D, 37, because we've solved the modular multiplicative inverse calculation, and those were co-prime, that means we can get an answer of 1 for that. Let me just reduce the size of these down a wee bit so we can get them all on the screen. So we have everything we need for the algorithm. Okay, we have everything we need. We have P, Q, N, phi, E, D, M. Oh, we don't have an M. We don't have a message. So let's go easy again, and let's try and encrypt 4 with these. We'll stick with 4 as our M for our first test. So let's try and encrypt 4 using these numbers. Okay, now I think I've put another slide in, and so we're on slide 24. I think I've put a slide 25 to test this out. Okay, and I have. So let's go back and just fill these out. So N is going to be 77. N is 77. E is going to be 13. D is going to be 37. And M is going to be 4. So that's all we need. That's all we need. We don't need phi anymore. Well, we do actually need it later to work out D, but for now we're all right. We're all right without phi. So let's encrypt 4 using this E here. So we're going to do, okay, m to the power of E mod n is going to give us something. So let's work that out on the calculator, okay? So m is 4 to the power of 3 is going to give us 64, as it did before. Mod n, mod 77. 64 mod 77. So let's go 4 to the power of 13, first of all. So 4 to the power of E gives us this huge number here, right? Mod n, and n's 77. Mod 77 is going to give us 53. Okay, so this number is the encrypted number, and we've encrypted that with the public key. So now we're going to say, hi Alice, we use Alice this time. Hi Alice, I've encrypted a number with your public key. I'm going to send it to you over the network, and I want you to try to decrypt. Okay, so we can decrypt this just by doing, okay, m, which is now 53. I'm going to take a little note of this on my notepad. M to the power of D mod n. Okay, so m is 53 to the power of D, which is 37, mod n, which is 77. Now, that's a horrible sounding calculation, isn't it? Imagine if someone said that to you on the spot. Right, so 53, we're trying to encrypt, we're trying to decrypt, so we'll use the decryption index of 37. 53 to the power of 37 is going to give us, so what we're going to have to do here is we're going to have to use the big number calculator. So let's just keep this in mind, 53 to the power of 37. Let me just copy that. I'm going to take you back a slide to here, and we're going to go to this website, the big number calculator. Sounds very intimidating, doesn't it? Okay, so 53 and to the power of 37. So x to the power of y we want. There. Look at that number. If anyone ever says to you, what's 53 to the power of 37, you could say, oh, that's an easy calculation. Right, so we've got this number here. This is a very, very big number, okay? So there, we have we have that number. So that, apparently, let's go back to here. So that is message 53 to the power of the decryption key. And what I would say is, if this works, right, if we get 4 as an answer, then this shows that the key pair works, okay? So that giant number, mod 77, should give us 4. Okay, now I'm not sure if the big number calculator can do it. Oh, it can. It can, look. So let's do that in here. Okay, x mod y. Okay, and n is going to be 77. So let's go 77. Right. What will the answer be? What do we think the answer will be? Right. Let's try it. Okay. This might go wrong. Ah, look, 4. It's the answer. It's 4. Look, see. So that giant number there, mod 77 gives us 4. So that shows that the encryption has worked. Okay, the decryption has worked. So we received the message encrypted with our public key, and we were able to decrypt it with the private key, and we got the result of 4. Although we had to do this mod 77, and I can't even say that number. Okay, I think that number was, what was the actual? So 6.2 times 10 to the power of 63. So unfortunately we had to go through that to get the number back out. And this is why this is a very difficult to crack encryption algorithm, because really we started off with 2 prime numbers, 7 and 11, and we were able to use those to generate n, phi, e, d, and then we created our encryption key, public, e, and our decryption key D, and we were able to prove that we could decrypt the numbers with that. Okay, so what I'm going to do now is we'll ramp it up to slightly bigger numbers. Okay, we'll take bigger numbers because we've got this handy big number calculator here. Okay, so we're going to do work through another example. Okay, so let's call this example 2. Example 2. Right, we filled out that. Let's go to example 3. So we got a blank slate here. So let's pick some slightly bigger primes. Let's go slightly higher. So I'm going to say P we'll start with 13 and Q can be 17. Okay, so they're both prime. So step 2 is work out N and Phi. Okay, so let's work out 13 times 17 to get the product. That's 221. So N will be 221, and Phi is just 12 times 16. So let's do 12 times that by 16, and that gives us 192, so Phi will be 192. A favourite among IP addresses. Right, so now all we need to do is work out E, and to do that we're going to list the factors of Phi and the primes of Phi. So let's grab Phi and head over to our prime number calculator. So Phi is 192, so we want prime numbers from, let's say, 1 to 200. And generate that on this horrible website full of advertising. And let's get the factors of 192 from this slightly nicer website. So there's our factors there. So we've got our primes here. Here's all the primes, all the way up to 191. And here's our factors here. So we need to pick, to find E, we need to pick a number, okay, that isn't a factor of Phi. It has to be a prime, but it can't be a factor. So let's look at the factors. We've got 1, 2, 3, 4, 6, 8, 12. And the primes, we've got 2, 3, 5, 7, 11, 13, 17, 19, 23. Let's pick 23. Because that's a prime number from 1 to Phi, but it's not a factor. So let's go 23. So 23 is E. Easy. Done. Right. Next thing we need to do is work out the modular multiplicative inverse. And to do that, we need to solve D times E mod Phi equals 1. But luckily, we've got a nice calculator to do that. Let's calculate this. So to calculate this, we just put E in here and Phi in there. So E was going to be 23 mod Phi, and Phi is 192. And that should give us, that'll solve it for us, right? Calculate. There we go. So 23, believe it or not, times 167 mod 1. So D is 167. So let's go back and put that in there. D167. Right, I'm going to make these a bit smaller font so that they fit on the screen better. And I think then we're going to be good to try out our favourite number, 4. Let's encrypt 4 with this fun set of numbers. Okay, so tell you what I'll do. I'll just do this onto Sublime so we can see the numbers and we can see what's going on with Sublime. So to encrypt 4, we're just going to do M to the power of the encryption key, the public key, mod Phi, mod N. Okay, so let's do 4 to the power of 23 mod N is 221. Okay, so 4 to the power of 23 mod 221. Now this is probably going to be, again, a painful number. So let's first of all work out 4 to the power of 23. So 4 to the power of 23 should give us, that's going to be too big, right? We need to get back to the big number calculator. 4 to the power of 23, where is it? Right, 4 to the power of 23. And let's just do x to the power of y there. Okay, that's a big number. That's a very big number. Right, so let's pop that in there. And we're going to say that that number, mod n, is going to give us our encrypted value. Okay, that's going to be the encryption. So n is 221. Okay, so let's go back to the big number calculator, 221, and we just want to do mod 166. So the encrypted message is 166. Okay, we're encrypting it to 166, so put in brackets 166 after encryption. So now, to check that our key pair works, we're going to send 166 over the message, over the network to Alice, and we're going to say, hi Alice, I used your public key and I encrypted 166. I encrypted a message and it's 166. Go and decrypt it so you can get the secret message out. And Alice would say, sure, I'll just use my private key to do that. So in order to do that, we're going to do m to the power of d mod n. Right, so m to the power of d mod n. So let's work that out then. M to the power of d mod n. So m's 166 to the power of d to the power of 167. That's fun. Okay, so 166 to the power of 167. Let's go power. That's probably equivalent to the number of cat pictures on the internet. So let's copy that, pop that in there, and apparently that number mod 221 should give us the answer back out. We'll see what it comes out as. I'm totally 50-50. I'm actually swaying on the side of it. It's just impossible to tell, isn't it? How can you tell what that mod 221 is? Right, let's do it. Close my eyes. So there we go. We decrypted it with the private key, and we get 4 back. Who would have thought that that number mod 221 would give you 4? You just couldn't make that up, could you? Well, I'm not making it up because it's true. That number mod 221 is 4. So that's an example with slightly bigger numbers there.